you'll know that the homework is the key. If you understand the homework, you do the homework, and you're familiar with how to do it, tests are usually not a problem at all. People usually do very well. If you've been blowing off the homework and you try to cram, is where people get confused and in a lot of trouble in my class. That's the only thing I'm going to tell you. And how many have had me before? Anybody? You have. No one else? Okay, well, if you talk to people, you're going to see that the secret to success is keeping up the homework and asking any questions about the homework when it's given the next class period. If you're doing that, you'll be fine. But it's not something that cramming usually helps, and memorization is the worst possible thing. It's brute force memorization. You're going to get confused as heck. I didn't go through all these quizzes, but I might as well go through the, before we start the next section of magnetics. Well, first, does anybody have any other questions? I was going to go over the quiz. Any other questions about it? Now, one other thing too, I try to say this, if you're going to start studying, don't wait till Thursday. Start now. All right? Start doing whatever you need to do. And remember, there's transmission lines on this test. There's the whole 9 yards. I mean, I'm going, just think about it. You've got transmission lines, Smith charts, right? Possible bounce diagram, unlikely, but possible. Then you've got electrostatics and everything that goes with electrostatics, from Gauss's law, point charges, capacitance, resistance. Follow me on this? And if you look at the homework sets they all build, there's nothing there that doesn't seem to naturally come after the next section. Y'all with me? And there'll be probably one problem on magnetics that we cover. Something, you know, based on this first couple of chapters, or first couple of lectures on that. Now, any other questions before you go? You asked me about a quiz. Now, here's what I'm going to do, because I got several people, and this happened a lot during COVID, where I get all these people that need makeups. So what I'm going to do is at the end of the semester, before the last, say, second to last lecture, I'll give a collective makeup to anybody that needs it. Follow me on that? And that test, that score will be used for your makeup for any score that you've missed. Got that up? All right. And can I think of anything else? Is anybody traveling with the team in here? Basketball. Okay. That's the only problems I've had in the past. I've had people that were traveling with the team either they were football with band and stuff like this, or players, but I don't get many 5-star athletes in here in basketball or football. Not usually. I get some swimmers occasionally. All right. So I want to go over the quiz with you this time, because I think there were people that misunderstood the way to do it. These were simple things that we went over in class. Right? I'm going to just break the problem down. If you have, doesn't matter if it's a cylinder or a sphere, if you have inner radius A, outer radius B, and I divide this into 2 layers, and I'm going to say this is epsilon 1, sigma 1, and this has epsilon 2, sigma 2. Now, I divided it in half, and it was a sphere. Do y'all follow me on this, class? So first thing I'm going to do is put down what is the capacitance of just the sphere of inner radius A, outer radius B, filled with epsilon. Y'all remember? What was it? It was 4 pi epsilon, right? This is just for a sphere with a constant value of epsilon. And it was what? Divided by, you remember? 1 over A minus 1 over B. Isn't that right, class? How many remember that? That's the capacitance of a sphere if it's got an inner radius A, outer radius B, filled with epsilon. Now, for the resistance between the inner and outer conductor, you remember how I told you to get from that? This is just going to be constant sigma. Matter of fact, let me make sure I said this has to do, these 2 formulas have to do with this problem. So it's the resistance between A and B, or the capacitance between A and B. Now, for this, I told you there's a trick. What was it? Do you remember? It was RC, or CR is equal to what?
Epsilon versus sigma.
That's right. That's a good thing to know for the test. Hint, very good thing to know for the test. Anytime you have an invariant value of sigma and epsilon, and you know the capacitance between the plates, you automatically know the resistance between those plates. If you knew the resistance, you would know the capacitance. Y'all follow me on that? It's a very nice trick. So here, I know the resistance here is just epsilon, right, over C sigma. Or I can take a look at this, it's epsilon above over 4 pi epsilon. And then this is going to be 1 over A minus 1 over B. And then it's going to be divided by sigma. I literally put it down the way you should have had. This is something I want to make sure you see. Now the epsilons have to cancel. All right? Resistance is not a function of epsilon. Then when you take a look at this, I got what? I get 4 pi sigma, right? And then I have 1 over that, or I have 1 over A minus 1 over B. Done that, class? Are you with me at that? Okay, so now back to this one. Now for this problem, here's how I'm going to just, for the capacitance, you all agreed that the capacitance for the whole thing is given by that. So for half of that would be half that value, right? Y'all follow? So what I'm going to say is the capacitance of the whole system, or total, would be as if the whole system was filled with epsilon 1 divided by 2, plus as if the whole system was filled with epsilon 2 and this divided by 2, or the total capacitance, because they're in parallel. Do you all agree with that? Parallel capacitances, you would add as if there were resistors in series. And for this one, it's going to be 4 pi, and I can take the 1 over A minus 1 over B out in front, and then I'm going to have this times 1/2, and it would be epsilon 1 plus 1/2 epsilon 2, and that would be the actual capacitance of the system. Do you all agree with that? Now that value of epsilon is epsilon relative epsilon naught. So I should make it clear that epsilon here is epsilon relative epsilon naught, and epsilon naught is 8.854 times 10 to the minus 12 farads per meter, or 1 over 36 pi times 10 to the minus 9 farads per meter. Either one. All right? That'll be the capacitance total based on A and B, epsilon 1, epsilon 2. You all follow? Now for the resistance total, the resistances are in parallel. So there'll be some R2 and R1 here. Do you all agree with that? So the resistance of this one or this one would be the resistance as if the whole thing was filled with sigma 1 times 2, right? Because it's half the plate area. Do you all follow me on this, class? How many see that? So when I do this, the total resistance is going to be the parallel combination of 2, I'll put the parallel symbol, times the resistance, which is down there, sigma 1 in parallel with 2 over 4 pi sigma 2 times 1 over A minus 1 over B. I did it this way for a reason. This means just in parallel. So I've got the first resistance and the second resistance. Do y'all follow me? Now, at this point, how you do this is up to you. A lot of people are used to just taking R1 times R2 over R1 plus R2. Y'all remember? You can do that. It may be more work than it's worth. If I come over here, I can say the total resistance here would be equal to, well, now I'm going to take 1 over, first I'm going to simplify this just a bit. I'm going to make this a 2 here, and I'll make that a 2. And then the only thing I'm going to do is take 1 over the first one plus 1 over the second one. So now I get 1 over, and 1 over the first one is 2 pi sigma 1 over 1 over A minus 1 over B plus 2 pi sigma 2 over 1 over A minus 1 over B. And you can leave it like that, or if you want to, you can multiply the top and bottom by 1 over A minus 1 over B and get it on top. Doesn't matter, but that would be the right answer. Do you all follow me? And I'll post the solution. Somebody asked me for that. I'm just going over this to make sure everybody follows me. I think the mistake was made right here, where instead of doubling the value of resistance, you have to. That's the only thing I can see. All right. So that's that. Now, did you have any questions at all about what we've covered so far with the magnetic field? We've done basic calculations, right? We've got the magnetic field for a differential length of line, then the magnetic field for a loop and an infinite wire. Do y'all remember that class? Those are the ones we did. So after that, I'll tell you where I am in the book, and I'll show you what we're about to do. I'll do the solenoid next time, or if I have time later. What I wanted to do I'm going to go through Ampere's circuit law, and then I'll go through the sheet of charge, or the infinite plane of current density, and also the solenoid. But I want to go through Ampere's law because it's so important. So this is Ampere's law. Now this contrasts exactly to Gauss's law, and I'm going to show you why. If I put Gauss's law here, remember with Gauss's law, it said the integral of d dot ds, this is the integral form, over any closed surface, was the actual Q enclosed by that surface. Y'all remember that, class? Gauss's law is very important. It allows us to really do minimal amount of calculations to calculate the D field and then the E field for any kind of simple geometries. Infinite planes, spherical surfaces, or infinite cylinders. It's easy to do, or line charges. Ampere's law is similar. Ampere's law says this: the integral of H dot dl around a closed, this is a loop, a closed loop, is equal to the I enclosed by the loop. Now I've got to show you examples of this, because that mathematical statement doesn't mean much in itself. Now, do you all remember when you had Ampere's law? How many do? Good. Let me say one more thing before I just start off on that. Here, we know this is the integral form of Gauss's law. Does anybody remember the differential form of Gauss's law? Anybody? That's obviously, it's an integral. It's the integral form. What? What's it? Well, all right, it's divergence of D, nevertheless, is equal to rho V, right? Its divergence of D is the charge density. Do y'all remember that? This is the integral form. Well, the integral of this over a volume would be the integral of D dot ds over a surface, or it's the electric flux, and the integral of rho V over a volume would give you the charge. Over here, the exact parallel to that is going to be the curl of H is equal to J, the current density. So just I'm trying to organize this in your mind so you see the parallels. It helps when you're doing problems and actually understanding things. Follow me? Now that's a curl operation, that's a divergence. And I could step back one more place and say, do you remember when you had just the point form of the Biot-Savart law, you remember that E or D, that E was just equal to, no, I'm going to leave that alone. If I start down that trail, I could open up too many cans of worms. But do you all remember how the one big difference between magnetism and charge in terms of, or just static charge, the effects of the field quantities, either D, E, or H, were that has a cross product operator over there. Do y'all remember that? That's important to keep in mind. So now, when I talk about this, with the integral of H dot dl over any closed loop is equal to I enclosed, the best thing to do is showcase what I mean by that. So if you take a look at an infinite current I on the z-axis, you follow this? This is going to be on the z-axis. And now I come out a distance rho. This requires you to have some, you remember with Gauss's law, you had to understand that the D field, the way it would actually be mapped, you might say, it has to be in the radial direction, correct class? I come over here, and if this is X here, and this is Y here, and I come out any distance away from their rho, the magnetic field will always circulate around this way. And I'll try to explain why. This would be the direction of the magnetic field. If you remember that dH itself was equal to I dl crossed into AR over 4 pi r squared, right? Do you all remember that? That was the differential magnetic field from any chunk of current. Well, if you look at this thing, you can take any point here, and if I go out, come to this point, IDL is this way, it's going up, right? Crossed into R would be a magnetic field going into the board there. Do you all see that? Can you imagine if you take IDL this way, remember the right-hand rule, put your index finger in the direction of the current, crossed into the radius vector R, or AR, your thumb points in the direction of the magnetic field. Now you'll see if I'm out this way, if I come out of the board and I do IDL crossed on it, it's this way, right? Here, if I do IDL crossed on, it's this way. And in fact, the magnetic field will always be perpendicular to the radius vector, it's perpendicular to that axis, and it will be perpendicular to the actual current's direction. So it's got to be in that direction, or the A phi direction. Does this make sense what I'm saying to you? All right. Magnetic field will only be a function of radial distance away, not of height. If that's infinite, that should make sense to everybody. If it's an infinite wire, if I'm here or here or here, the wire looks the same length, right? It's infinitely long. The only thing that determines the H field will be the distance from the actual axis, the radial distance. Does that make sense to everybody? So now if I put down that law, the integral of H dot dl around a closed loop is equal to the I enclosed. I hope you appreciate this right here. Well, when I look at H dot dl, what am I really talking about? The perimeter of a circle of radius rho here. Do you all see that? Or of radius r if you want r, but I prefer rho because that's cylindrical coordinates. So you come down here and you say the integral of H it would be in the phi direction, and dl here would be rho d phi if you want the formal way to do it. Dot dl, and it would be in the a phi direction. Dot dl, actually dl would be, I wrote this wrong, here's what it would be. You don't need to correct it. Let me just explain this. H itself is unknown, so it's H phi, A phi. We know it's going to be in the phi direction based on arguments of symmetry. Then it's dotted into dl. Well, dl would be rho d phi, A phi, and it would go from 0 to 2 pi. That equals the charge or the current flowing, which just would be I on the axis there. Now, if you look at this, this may not make a great deal of sense, but if you think about this, when I take a look at something, I'm out of radial distance rho, and I wiggle that thing over phi, you get rho d phi as the length of the tip movement. Do you all see that, class? Everybody? Remember that? So here, the a phi's will dot out, and I'll be left with the integral of rho d phi from 0 to 2 pi, or I get 2 pi rho times h phi is equal to the I enclosed, or h phi is simply equal to I over 2 pi rho. And that is correct for an infinite length without doing any crazy calculations. Remember how I did this last time? Somebody remember how I got the h field at a distance rho away from a line? Do you remember doing this? What did I do? I took a differential length here of I dl, and dl was dz az, right? I put it in that formula. Then I got my radial vector r here, right? That r would be what? It would be rho a rho minus z az, right? We assumed this was at 0. Do you all remember doing this? Then you had to do this cross operator. And after you did that cross operator, you had to integrate from minus infinity to infinity. You all remember doing that? That's work. This isn't, but it requires you, if you're going to use this, Ampere's law, effectively you have to realize that it's for problems with a high degree of symmetry where you can exploit symmetry. Now, you all agree that all the current through there is I, right? And when I say current through there, I mean penetrating this imaginary surface of a loop. Do y'all follow me? You can only use this for problems with high degrees of symmetry. If you think about another problem you could do, I mean, you can do this for what Dr. Wentworth likes to do in his book is have pipes of different radius, thin pipes with currents flowing up and then down and getting the H field. I'm going to do that next because it really kind of helps you see what I'm talking about when I do this. And I know when I'm putting just general mathematical statements on the board without applying them to problems, a lot of times you're not sure of how you'd go about doing it, and I know that. So, now, let me take you to the next kind of problem. This one's a little interesting. So, suppose I have a pipe. What I'm going to do is this. Yeah, I'm going to have a pipe, a thin pipe at radius A, and then I'm going to have an outer pipe out here at radius B. Call them infinitely long for now. I'm just trying to give you a mental picture of what I'm talking about. Now, on this inner pipe, assume it's infinitesimally thin, just assume it's like the wrapping on a coax cable. If you know how there's an inner core, solid core, then there's an outer foil wrap, right? Well, assume on this inner one there's a current I going up. And on the outer pipe right here, there's a current I coming down. Y'all imagine that? Now, assume it's on the z-axis. And now what I'm going to do to make the problem a little easier to see is I'm going to look right down the z-axis. So I'm going to look from above straight through. And if I did that, I'd see this. this would be radius A, this would be radius B. If I'm looking down the z-axis, I see this current coming up. And the way they usually indicate this is just circles with dots in it. Remember, the total current flowing here is I. And then the outer one, they usually just indicate this with crosses and circles. I was told years ago this came from imagining an actual arrow going through a target. If it went all the way in, you'd have feathers like this. If it was coming at you, you'd see a dot. Put a circle. And this current is going down, this current's coming up. Can you all imagine that, class? Everybody see what I'm talking about? All right. I mean, how many can? Right. Just want to make sure. So now we're going to apply Ampere's law. First, y'all agree that's very symmetric. Cylindrical symmetry is obvious, right? The current itself is cylindrically symmetric, where we've got really just circles I'm looking at there. So the law says this, Gauss's law, Ampere's law says the integral of H dot dl around a closed loop is the current penetrating the surface enclosed by that. So let me go through here and apply it. The first case would be for rho less than A. So now think about this. I'm going to come here. My rho is less than A. I want to make sure y'all can see what I'm doing, right? Now I draw, and they call these Amperian loops. You know how you have Gaussian surfaces? Well, these are Amperian loops. They're imaginary, but it's a loop nonetheless, and it's symmetric about the axis. When I take a look at this, I know that the integral of H dot dl will be equal to I enclosed. How much current is penetrating this loop right here? Can you all see that? It's as obvious as it seems. Is there anything flowing in there? Nothing, right? I have to get to A or better than A for anything to flow. So it's 0. Well, if it's 0 here, H dot dl will always be the circumference, or it'll be simply 2 pi rho times h phi equals 0, or h phi would be 0. You all see that? No current, if your loop doesn't have any current coming through, it's a symmetric problem, the H field is 0. Do you all follow me? Now, next, we go through part 2 of this. Now we're going to have a radius greater than or equal to A, less than B. So here, see if anybody can help me with this one. Now I'm right here. I'm between A and B. Here's my radial distance. All right, now I apply the loop. You all follow me? I'm going to go ahead and put my Amperian loop here. Some loop. Right. All right, this is going to be at a radius rho. Y'all follow me? And I know this would be my H dot dl surface all around there. So when I take a look at the integral of H dot dl around that closed loop is equal to I enclosed, you see, I know it's I because I've got I uniformly distributed on the radius A. Do y'all follow me? All that current is flowing on the outer edge of that pipe of radius A. So this is just I. Anytime you're dealing with cylindrically symmetric stuff, the integral of H dot dl will always be 2 pi rho. It'll be the circumference. 2 pi rho times h phi is equal to I. And therefore, h phi here will be equal to I over 2 pi rho. And that will be true between A and B. Can you all imagine that in your head? Take a moment and force yourself to think about this. Does that make sense to everybody? The last part, think about, don't answer out loud yet. The last part is, what happens when I'm in the region rho greater than B or equal to B? Now I'm out here, right? This is my rho. Now, and this would be my path integral of H dot dl, right? What can you tell me about the amount of current that flows inside that bigger one? What is it? Zero, right? Whatever's flowing up through it, one way is going the opposite return current, right? This is an important concept. That means no net current passes through that surface, all right? Which means it's zero. So the integral of H dot dl here over the closed loop is zero once I'm outside that. And it means that H is zero. By the way, this is a very important concept that I'm showing you, because for coaxial cables and any other cylindrically symmetric cabling that's in a differential mode, you all know when you have like an extension cord or anything, the same amount of current going one way is coming back the other, right? It's differentially driven. Well, the coax cable, the nice thing about it is that the fields, the H fields developed outside of it are zero because of Gauss's law. Gauss's law says if there's a straight pipe and the current's symmetrically distributed, the amount of current going down the interconductor is flowing back on the outer sheet at all times. Do y'all follow me? Same amount? The H field is zero, which means that it's also something that is not radiating. And that means that it's very good for electromagnetic interference and electromagnetic compatibility work. You all realize when you deal with any kind of cabling that has to do with communications equipment, TV, stuff like this, it's coax cable, or it's HDMI. HDMI is also a cabling, the way it's done, that has no real field emissions outside. It's fairly unsusceptible to external radiation causing anything. That's important. So remember, whereas if you just have two wires coax, or two just parallel wires, like an extension cord, those things radiate all over. There's fields all over them, and they're very susceptible to any kind of interference. So that's why coax is so good. I'm trying to just give you a little more insight into why this is important. So that's just the standard way of figuring it out for anything with cylindrical symmetry. And I want to tell you one other thing. Almost all the problems that you get that are of interest to give for tests, quizzes, are cylindrical in nature. Do y'all hear me on that? I can tell you that yes, in fact, you can apply this law to planar geometries, but they're not very interesting. Now, I am going to go back and deal with the solenoid and deal with the planes in a second. I want to tell you this, that the problem that I described, well, at least in part, is shown on page 230, but you'll see that really almost all these problems can be dealt with in the same way that I showed you there, is figuring out how much current penetrates the Gaussian surface. And I want to do one other one. This one I'm not a real fan of doing it this way, but it serves a purpose. So if we have a solid pipe of radius A, infinitely long, centered on the z-axis, all right. Now this is a standard Whitworth problem. It's something you could expect on an exam. Then what I'm going to do is say I have a current I uniformly distributed over the cross section of that pipe. It's going up the z-axis. Can you all imagine that? And what I want you to do is determine the H field at any radial distance. So at a distance rho, I want to know the H field for everything. Got me on this, class? So focus on this. So the first thing is I'm going to have to divide up the regions. Since I know that I've got a solid pipe here of radius A, this is solid. All the current's confined to that, but it's uniformly distributed. Y'all follow me? So I can say that J would be equal to simply I over the cross-sectional area. Do y'all agree with that? If it's uniformly distributed. So what is the cross-sectional area of a plate of radius A? Area. It would be what? Pi A squared, and this would be in the AZ direction. That would be amps per meter squared. Do y'all agree with that? So now I've defined the current density. This is true, right, for rho less than or equal to A, greater than or equal to 0. And then J would be 0 for rho greater than A. Do y'all agree with that? Because the current density has to be 0 if it's contained inside that water. You follow me, everyone? All right? We've got that down. Next, we apply Gauss's law. The obvious, you might say, way to partition this is for rho less than A and then rho greater than A. Do y'all follow me? So for rho less than or equal to A, I know that the integral of H dot dl would be equal to the I enclosed, right? Y'all with me on that? So now, what I want to do is draw this pipe looking straight down so I can make some comments that are a little more applicable. So if I look right down that pipe, it has a radius of A. And now what I'm going to do is say, if I come out a distance rho, I know the integral of H dot dl over this pathway would be equal to the I enclosed. Do y'all follow me? All right, now the integral of H dot dl, first of all, it's a highly symmetric problem. The value of H here is going to be the same all the way around a loop with constant radius rho. Do y'all see that? You can make all sorts of arguments for that. Imagine yourself at this point and then spinning the actual cylinder. It looks the same always. Therefore, H has to be the same. We can argue that, but it has to. If everything looks the same for all possible azimuthal angles, the H field has to be cylindrically symmetric, and it'll be the same magnitude. All right, what is this always going to be in cylindrical coordinates? The integral of H dot dl is over a cylindrical perimeter. It's the circumference 2 pi rho, right? It would be 2 pi. You all understand that that is the circumference of a circle, or the perimeter, right? 2 pi rho times H phi. And that's equal to I enclosed. How do I figure out how much current goes through here? I've got a radius rho. Class? Think about it for 1 second. Well, couldn't I integrate the current density over the surface? Everybody with me on that? Sure. Do I have a current density?
Yeah.
Right? I could say that this is I enclosed, which would be equal to the current density, J, I'll put it down just generally, J dot ds. So then you have to ask yourself, well, what would be a differential surface here? If we're in cylindrical coordinates, do you remember what a differential surface is in the xy plane? It would be what? Rho d phi, that would be the white arm, times d rho. That would be going out radial. Y'all follow me on this? So it would be j dot, and then it would be rho d phi, and it would be d rho, and it would be in the a z direction. Now this is j is going to be in the z direction too. I'm going to go ahead and put this down one time. So I gave you j. That's I over pi a squared. It's in the az direction. That's this. Now I'm going to multiply this by simply rho d phi d rho az. And first question is, where does phi go from in this surface integral? Where does phi always go from? 0 to 2 pi. Where does rho go from? 0 to rho. Y'all follow me? This is one of those things, it doesn't go to A. We're not there yet. It only goes to rho, right? Our surface right here, it's how much current penetrates the surface of radius rho. Now the truth is, you're not allowed mathematically to have limits and the kernel of integration have the same symbol. So they usually just prime that right there. And they'll say it goes from 0 to rho. Y'all follow me, class? That's just, we're engineers. Engineers don't care about that because they're not mathematicians, they want to get answers. So they would do that integral and then use rho there twice. So az dot az is 1, right? I want to make sure about this. And therefore, I get this to be equal to what? I over pi a squared. Now, if you look at this, when I integrate d phi from 0 to 2 pi, I just get 2 pi, don't I? And then when I integrate phi prime d phi prime, I get phi prime squared over 2 from 0 to rho. Or I simply get what? Rho squared over 2. Y'all, are you with me what I'm up to? And that would be equal to this. 2 pi rho h phi. Now, I'm just going to leave this h phi here. I want to mention one thing. What I'm really doing here, because j is a constant, isn't it? Take a look. I'm just taking the value of j by the surface area here, right? Surface area at radius rho would be pi rho squared, wouldn't it, class? And if you look here, what happens? Well, these twos cancel, and I'm left with I here, the pi's cancel, and I got rho squared over a squared, and that's equal to 2 pi rho h phi, and that means h phi here is equal to, if you look at this, I'm not trying to confuse you, and I'm sorry this is a little sloppy, but this is what this integral, the total current integral equals. That's what the perimeter equals, the perimeter integral equals. And if I go ahead and divide by 2 pi rho, I get this to be equal to I rho over 2 pi, and then it's going to be a squared, because the rho squared and the rho cancel. Do you all see this, class? Can you all see it? Now that's true for rho greater than or equal to a, less than or equal, or I'm sorry, greater than or equal to 0, less than or equal to a. I always tell people, try to check your answers when at all possible when you're doing this. Does this make sense? Well, when rho equals 0, what is the H field? Just look. 0. It's 0. Does that make sense? Yeah, sure. You're right right at the center of the wire, right? There's no real current there to speak of as a singularity. Now, when rho hits A, what happens? This is important. Well, when rho hits A, I get what? I over 2 pi A, right? Do you remember what the current, or what the H field is? If I have an infinite line of current and I'm a distance rho away, it's just I over 2 pi rho. Do you remember that? In fact, something you can glean from that is now, remember this is true for this region, when we go out to the second region, rho greater than A, and you think about this, integral of H dot dl around a closed loop is equal to the I enclosed by that loop, right? Now, just look at this. Now I'm out here. Right, that's my Amperian loop. How much current penetrates that surface? All of it, I, correct? I started with the assumption I have I. Y'all follow me? And that means over here, this is just I. And what's this? I try to beat that into you. The integral of H dot dl around a loop is 2 pi rho H phi. And therefore, H phi would be equal to I over 2 pi rho A phi. And as a matter of fact, you knew that from before, didn't you? Because if you remember the infinite line, you may not remember because you weren't bright, but we did the very current, or we got the H field from an infinite current. How many remember at least doing it, whether you remember the formula or not? All right, if you do, that's important because you're seeing how Gauss's, or this law, sorry, Ampere's law, is giving us the results we already know in a lot of cases. We know that. That's true. And this is another thing I'm going to say. Anytime you have current that's cylindrically symmetric, it's distributed that way, and it's in a cylindrical system, it's infinitely long. As soon as you get outside where the last, you might say, current distribution exists, you can take all the current penetrating that Amperian loop, stick it at the origin, and just say, that's just like you can get the H field out there as if all that current was on the axis. You don't have to worry about calculating the H field from one current source, another, and another. Just add them all up, put them on the axis. As long as you're outside the region where the last current, you might say, distribution exists. So if you had 3 layers, you'd have to be outside the 3rd layer. Then that would work. But I wanted to cover that today. Now, we'll go through the solenoid and go through the infinite plane. They're very easy to do now that you understand, or have seen Gauss, or seen Ampere's law. So I'm going to give you some problems on this. On Wednesday, we'll do a review for the exam on Friday. I'm sorry about that. All right. If you have questions, you can see.